The topic of this video is a brief introduction to incomplete dissociations and chemical equilibrium. In previous videos, I've discussed the use of unidirectional arrows to describe chemical reactions that proceed completely to the right. We use some of these examples: the dissociation of magnesium chloride and water, which dissociates fully into magnesium ions and chloride ions, the decomposition of calcium carbonate, as well as the combustion of methane. These are examples of reactions that proceed quote-unquote completely to the right. All reactants are consumed to produce nothing but products. In this example, we're going to begin to discuss the use of bidirectional arrows, as seen here. These arrows indicate that this reaction proceeds both to the right and to the left. So reactions that use this notation do not completely proceed forward. One example of this is the dissociation of sodium acetate. So the forward reaction described here demonstrates that when placed in water, sodium ions will dissociate from acetate ions and float around in suspension. While this is occurring, however, acetate ions are reassociating with sodium ions to form solid sodium acetate again. So we have the forward movement of this reaction and the forward movement of this reaction. So while these two are occurring together in unison, this is an example of a chemical reaction that has reached equilibrium. The forward reaction is occurring while the reverse reaction is simultaneously occurring to varying levels of both. Now this may sound slightly confusing, so let me try and use an example that may make more sense. So it's no secret to anyone that I enjoy fishing. So let's try and use the movement of fish through this object as an example for chemical equilibrium. And to simplify things, let's begin by focusing only on the forward reaction of the dissociation of sodium and acetate ion here. So you can think about this. As sodium and acetate are placed into water and begin to dissociate from each other, the fish are swimming through this little object channel block here, right? As more and more ions dissociate, more and more fish are swimming to the right. However, in a chemical reaction that ends at equilibrium, as the forward reaction occurs and products are produced, technically products tend to undergo the reverse reaction. So here, the reassociation of sodium and acetate ions. And this can be represented as fish moving backwards through the channel here. At some point, depending on each chemical reaction, as the balance of reactants and products becomes shifted in one direction or the other, we get this occurrence, where fish are now swimming both forward and backward simultaneously. And so this represents the equilibrium achieved of this reaction. As the reaction proceeds forward, the reaction also proceeds backwards, and this occurs at an equal rate once the reaction has, again, reached equilibrium. Now let's use an example that maybe you've seen before: the production of nitrogen dioxide from nitrous oxide. So as this reaction occurs forward, we have one molecule of nitrous oxide that breaks down into two molecules of nitrogen dioxide. And as the reverse reaction occurs, two molecules of nitrogen dioxide form one molecule of nitrous oxide. And again, this chemical reaction occurs in equilibrium, so as the forward reaction occurs, the reverse reaction occurs. And if you haven't seen this, you can check out this YouTube video link here, where you can see how heat influences the balance of this chemical equilibrium. So if we return to our fish example here, in this case, let's pretend we're starting with nothing but nitrous oxide. So the reaction will proceed forward because there is a large number of reactants. We'll produce a little bit of nitrogen dioxide, And then because of the unique properties of this chemical reaction at room temperature, and now as this chemical reaction has reached equilibrium, the reverse reaction occurs at the same rate that the forward reaction occurs. So we see this even trade of fish between reactants and products. So as one fish swims forward, one fish swims backwards. And if you notice, this chemical reaction, as it has reached equilibrium, there's a disproportionate amount of products as there are reactants. This is due to the unique chemical properties of the transition of nitrous oxide to nitrogen dioxide. This chemical reaction technically favors the reactants here. So one unique thing about chemical equilibrium is that if you start with a large number of reactants, again dependent on the unique properties of this chemical reaction, we'll see a distribution of products and reactants that eventually balance out to represent the equilibrium. So here, if we were to start with a large number of nitrogen dioxide, we would see a rapid production of nitrous oxide until something like this occurs, right? So now we have our limited number of products and a larger number of reactants. And once this has occurred, the chemical reaction again will occur in equal exchange forward and backwards. So as the reaction proceeds forward, the reaction simultaneously moves backwards. And again, this is all dependent on the unique chemicals properties, which I'm going to explain in a few slides, because you may be wondering, how do we know which direction a chemical equilibrium lies? Fortunately for us, there's a way to measure and quantify this. So if the fish example isn't really making too much sense, try and think of equilibriums as a balancing act, kind of shown here in this cartoon, right? So in this case, our forward reaction is now the production of nitrous oxide, and our reverse reaction is the production of 2 nitrogen dioxide. So if we start with a large number of nitrogen dioxide or a large concentration, our reaction will proceed, in this case forward, will produce some nitrous oxide, and eventually will end at equilibrium, like here. Conversely, if we started with a large amount of nitrous oxide, our chemical reaction would proceed reverse in this case to produce some nitrogen dioxide and quickly reach equilibrium. So equilibrium, again, is when the amount of products and reactants, the total number of products and reactants, does not change anymore. There's an equilibrium, equal production of products and equal production of reactants in terms of these reactions. All right, so how do we calculate this, or how do we determine whether a reaction favors the production of products or the production of reactants? We can use a mathematical determination known as equilibrium constants. So if we again look at this generic chemical equilibrium reaction, and again our example here, the dissociation of sodium acetate, we can write the chemical equilibrium constant as this formula here. So KEQ, again, so this is the equilibrium constant. So this represents when the forward reaction and the reverse reaction are balanced and the chemical reaction is at equilibrium. We can write this as the concentration of our products in moles per liter, so C and D here. We raise our products to the coefficients in their balanced chemical reactions. So in this case here, C is raised to the power of C and D is raised to the power of D. So this is basically the concentration of the products multiplied by each other, divided by the concentration of our reactants multiplied by each other. And again, the same rules apply here. Our concentration of A, our reactant, in moles per liter, raised to the coefficient of its balanced chemical equation multiplied by the concentration of B raised to its coefficient in the balanced chemical equation. So what does this look like for the dissociation of sodium acetate? We have our two products. So here the concentration of our acetate ion with an exponent of 1, because that's what our coefficient in this balanced chemical equation is, multiplied by the concentration of sodium ions raised to the power of 1, again because that's our coefficient. So concentration of our products multiplied by each other divided by the concentration of our reactant. And here our reactant is sodium acetate undissociated. So we can put this together, and if we were given textbook values for this, we know that sodium acetate is a weak electrolyte. So we know it doesn't completely dissociate in water. So without giving you the exact number here, we know that KEQ comes out to be less than 1. And so again, because this example is a weak electrolyte, this allows us to also equate that KEQs of reactions that are less than 1 favor the reactants, right? So our sodium acetate solid here does not proceed forward and produce a large number of sodium ions and acetate ions. This reaction, chemical reaction, equilibrium, favors the reactants. How about if we look at our chemical reaction that we described earlier, the nitrous oxide being converted into 2 nitrogen dioxides? We would write the KEQ for this formula this way. So we have our nitrogen dioxide raised to the second power, again because the coefficient in this balanced chemical equation is 2, divided by the concentration of our reactant, nitrous oxide. And numerically, at room temperature, the KEQ for this reaction is 4.46 times 10 to the negative third, which is much less than 1. So this reaction at room temperature favors the reactants, similar to our example up here with sodium acetate. Now, because this is a chemical equilibrium reaction, what if we flip our expression around? So why don't we try this where nitrogen dioxide is our reactant and nitrous oxide is our product. This KEQ would be written like this, right? So now our products are nitrous oxide, so the concentration of nitrous oxide divided by the concentration of nitrogen dioxide. Again, remember, raised to the second power because of our coefficient. If we write our chemical equilibrium reaction and our KEQ formula like this, we have a KEQ, right around 224, which is much, much larger than 1, right? So when written this way, our chemical reaction favors the products. So this chemical reaction shifts to the right, and KEQ is greater than 1, so it favors products. So how we report KEQ is completely based on what we decide our products versus reactants are. And even though this is the same chemical reaction, again, remember at room temperature, the production or the formation of nitrous oxide is favored. How we write a KEQ affects the numeric representation of this. So the takeaway from here is, remember, when KEQ is greater than 1, the reaction favors the products, and when the KEQ is less than 1, it favors the reactants. In one of our next videos, I will cover the spontaneous dissociation and reassociation of water, as seen down here in this GIF. So in a solution of water, H2O, water is constantly undergoing dissociation, where one of these hydrogen ions pops off and attaches to another water molecule, forming hydronium and hydroxide simultaneously. And it's also simultaneously undergoing the reassociation, where that hydrogen will pop off of the hydronium and reassociate with our hydroxide. So the balanced chemical equation for this is H2O plus H2O will yield H3O plus, and OH minus. And again, this is an equilibrium reaction, so as it proceeds forward, it proceeds backwards. And this is going to be important when we start to talk about acid-base equilibria along with buffers.